in Arm. I'm based in Sweden. I just arrived yesterday evening. I've been awake since 2 in the morning, very fresh. So, if I get jet lagged in between, just excuse me. So when I submitted the title for the tinyML summit, I wanted to focus mostly on our efforts towards micro TVM on Ethos-U NPUs. But over time, I sort of realized that there is a need to sort of explain the broader strategy of where Arm stands in terms of our, how we are positioning ourselves in terms of the hardware and the software components that go into the IoT machine learning world. So this is going to be a broad, high-level view of how does Arm approach this whole tinyML space. TVM is going to be one part of it. So if we go through the sort of hardware, which is mostly commonly known in the ecosystem about what Arm does, which is the hardware IP, we have the Cortex-Ms. We started with the V7. Those were widely adopted. We ship billions of those chips today. Lots of devices that you probably know of are based on the early versions of Cortex-M. And then we moved on with the V8, which introduced the trust zone. And the latest ones to sort of hit the market are the ones with both trust zone and helium. So helium is our vector extension, which targets both signal processing and machine learning workloads. So if you look at the numbers here, you get up to 5x the performance when you use the vector extension helium, that is both the M55 and the Cortex-M85, compared to the normal V8 architecture. With machine learning, you get 15x the performance uplift. And this is based on matrix multiplication in int8. Now, with the MVE on, which we brand it as helium, you're close to the neon-enabled entry-level Cortex-A's. So we've done a lot of improvements in order to be able to run signal processing, that is classical signal processing, and also machine learning workloads on the IP itself. Apart from the Cortex-Ms, we also introduced the Ethos-U. These products, the Ethos-U55 and the U65, what we call as the microNPUs, they've existed for a couple of years. These are neural network accelerators, and we first introduced this as an ML island concept. So these integrate with the Cortex-M, very tightly coupled, but we also have the Ethos-U65, which is the next gen NPU that was released, which also is made for the Cortex-A integration. So you have DRAM there, which takes into the consideration of the latency issues. So that is addressed with the Ethos-U65 as well. So we do sort of take a broad range of, going from small, really low power resource constrained systems, which are Cortex-M only, to if you are running a little more complex workloads, adding on the Ethos-U. And also if you're running something with rich OS with the Cortex-A, then you can also run the Ethos-U65 NPUs. So basically what we've done is you get a whole broad range of different systems depending on what your system requirements are based on the power and energy efficiency that you're looking for. The Ethos-U and the Cortex-M are more than just the sum of two parts. You do get, of course, the benefits of trust zone, and you also get, as I said, unified software development tools and specific optimizations. This is a slide sort of taking everything into a single point here. So on the x-axis, you see the ML and the signal processing performance, and on the y-axis, you see the control code performance. So on the low end, you see the Cortex-M0s and M1s, and those class of devices, we've shipped more than 50 billion. That's 50 billion devices that are based on the Cortex-M only. There have been a lot of ML being deployed even without the MVE, but we did recently see, if some of you were in the embedded world, you would have seen that we have partners who are running computer vision ML workloads on the M85. So just by enabling the vector extension, you're able to run complex, much more heavier workloads for machine learning. And then you add the Ethos-U, and then you boost up the performance requirements much more as needed. Now, what I said on the hardware front, I think it's more or less known to the industry that in terms of Cortex-M, in terms of the NPU, we do promote a lot of our IP, but what we don't talk about often is our software and the ecosystem part that goes along with this. The software and ecosystem strategy is quite central to ARM. Let me give you some of the components that go into this. So we do open source most of our components. I think almost everything that we have in terms of the compilers, the reference kernels is open source. You can find it on GitHub. One of the reference libraries presented here is the CMSIS neural network library. This is part of the CMSIS pack, which is, as I mentioned, open source. You can, of course, get more details about this in the next room. We do have a poster there talking about how this integrates with our eval kit. But what this does basically is it provides you a reference kernel to optimize your neural networks so that the operators are much more performant when it's running on the Cortex-M. So as you see in the diagram, you have CMSIS DSP, which is part of the DSP components. If you have classic DSP algorithms, that's the DSP library you would use. But if you have neural network workloads, then it's a CMSIS NN that you would be using. So you can see the difference in performance when you switch on the CMSIS NN when it's used versus when it's not used. If you take the example of a MobileNet V2, you see 10x performance improvement just by using these software library components. And similarly, for a Wave2Letter, you get 11x performance improvement. This is based on a Cortex M55. So not only do you have a range of hardware components, IPs to work with, from low-end Cortex-Ms all the way to Helium enablement to the micro neural processing units, but you also have software components which can easily uplift the performance of your workload. Moving on, this is the typical workflow for deploying your neural network operators onto the device. So on the left, you see the offline host where you start with the framework. You have your model, you train it, and then once you have the model ready, you go through the model conditioning. Currently, we support the TensorFlow Lite. We've contributed quite significantly to the TensorFlow Lite model conditioning. We are, however, working with other players like PyTorch to make sure that their models are also quantized, and I think in the near future we should have something to showcase there as well. But you take the quantized network and the output is a TensorFlow Lite flat buffer, and you optimize that with our neural network optimizer. This is also an open source component, software component. We call this as Vela. And once that is optimized, you take that and then you deploy it onto your device. Now, the software component here seems to be a very small part of the entire tool flow chain, but it's extremely important because there's a lot of magic that happens here. It knows the architecture of the Ethos-U. It takes your operators and customizes them into a single customizer operator based on what is supported on the Ethos-U, and then it deploys it. It does memory scheduling based on the architecture, what Mac configs you're using. So it's it's extremely efficient to run your machine learning workload, compile it using the neural network optimizer. You do this offline, and then the output is run on the TensorFlow Lite micro runtime, and then you deploy that based on what is the operator set within the neural network. It either gets deployed onto the U55 or the U65 that is routed directly through the driver, or if it's not supported, then it falls back to the Cortex-M. So it's a seamless fallback from the Ethos-U to the Cortex-M, and there again you have different routes. You have the CMSysN and optimized kernels for you to get the performance uplift, as I mentioned previously. And if the operator for some reason is not supported there, then it falls back to the reference kernels that is part of the TensorFlow Lite micro reference kernels. Now, I think we support most of the commonly used operators can be easily accelerated on the Ethos-U NPU, and so it is with the CMSys neural network component as well. So by using the CMSys libraries, what we've basically made sure is that you don't have to separately work with your embedded code, the DSP code, and the neural network model. So there's no need to sort of work in different stages to deploy your system onto the hardware IP. We've unified this so that you can sort of use the open source libraries for CMSys NN, CMSys DSP, also the Vela neural network optimizer, and then seamlessly sort of deploy this onto your system using a single tool kit. So it makes it easier for you to sort of reiterate on your deployment and making it faster to sort of go to market. Now, one of the main issues that I see in sort of the IoT machine learning landscape is the pace at which it is evolving, and this sort of, since it's in early stage of development, there's a lot of issues with fragmentation of the machine learning frameworks. Now, one is the framework fragmentation itself. The second one is that it's quite difficult to get the same competence in a team where there is competence for both the embedded system knowledge as well as the machine learning sort of framework model and training expertise. So the data scientist does not sort of take into account where it is being deployed, and I think that is a big gap today, because you need to know the platforms, the hardware capabilities while you are developing your neural network. And I think there is a mismatch today. So these are the two main challenges that we see. So what did ARM sort of do is we said, okay, we do see potential with the micro TVM framework, where it sort of consolidates the different frameworks, machine learning frameworks, lowers it down to the relay IR, and then you get a binary component after the C source code is generated using the auto TVM, and then you can deploy it onto the system. So we've started to develop and execute and even contribute to the TVM community. As you'll see here, we have the ARM virtual hardware. This is also something that's in-depth explained in the poster in the hall next room, but I'll touch upon it quickly as well. So you can deploy machine learning workloads on TVM. This is the current status of where we are with our TVM development. So what we have done is we've first targeted the Cortex-M systems. Like I said, we have billions of devices out already in the market, so it was easy first priority for us to target the Cortex-M. So we've integrated the CMSys NN library onto the micro TVM. So you get the same fallback procedure even with TVM as it is with TensorFlow Lite micro. We've also deployed the micro TVM Zephyr RTOS support for Cortex-M. And this is, when I talk about the Cortex-M deployment in TVM, it is functionally and in terms of optimizations performant equivalent to what we support with TensorFlow Lite Micro today. So the Cortex-M contribution is out there. We've submitted that to the community. But when it comes to the Ethos-U, we've just about started, we just got started a couple of months ago. So we have added around 26 operators, as you can see here, some of the most popular neural network operators out there. And we continue to add them as we speak. We also have a demo app, which is uploaded into GitHub. You could go there and try out try running some of the models that are available there on TVM. We are also continuously, like I said, developing more operators and networks. So I think, I hope I'm not being too optimistic when I say that by the end of the summer, you should have support for most of these operators, most of these networks, sorry, on TVM and onto the Ethos-U. There's another component, that software component that we are working on, which is part of our research group. This is called TOSA, which is also trying to address the fragmentation of the ML frameworks issue. So TOSA stands for Tensor Operator Set Architecture. What it basically does is it takes your operators in the network and it breaks it down into primitives. So you can imagine your operators being built by fundamental Lego building blocks, and that's what it breaks it down into. It's a specification, it's not a tool, and the specification is now currently being accepted by different machine learning frameworks. We work very closely with Google. We are also collaborating with PyTorch so that their operators, when they deploy or when they develop new operators, then they make sure that it is TOSA compliant. What it basically does is it helps the IP to be numerically compatible, consistent with across the IP. So regardless of you running your machine learning workload on whether it's a Cortex-M, whether it's a microNPU, whether it's a A-class CPU, whether it's a GPU, you get bit exact numerical consistency across the IP. And this is what TOSA helps achieve. We also have a TOSA checker where you can take your neural network model and then sort of run it through the checker and see if it is compatible with the TOSA primitives. And if it is, then you do get the guarantee that this is sort of numerically compatible, numerically consistent with how the hardware behaves. So these are some of our sort of projects that we are working with. Some are in the engineering groups. They're already delivered. They're already upstream to the communities. We are constantly developing them, but some of them are still in the research stage. Like I mentioned, these are, we do have other sort of collaborations going on with PyTorch, with Paddle. We also have some sort of collaboration going on with the OpenXLA. There's so much movement happening with these whole machine learning frameworks. It's difficult even for a company like Arm to sort of keep up with the happenings. It's difficult to put all your eggs in one basket and say, okay, this is a particular machine learning framework that we are going to bet everything on, and then you see that there are other frameworks that are sort of evolving at a faster pace. So I'm super excited to sort of be involved in this and sort of have the driving seat view of where things are going. But one thing is clear, that we do very much think that machine learning deployment on IoT is no more a thing of the future. We do see a lot of deployments, lot of different use cases, both horizontally and vertically integrated. And Arm does think that this is going to be strategically important for our future as well. So that's it. That was my last slide. Thank you very much.